Good evening, and thank you for joining our third and final event relating to silk heritage in Spain. For those who don't know me, I am Claudia Hopkins. I'm the director of the Soberan Center at Durham University. First off, I want to thank Pedro Eusebio and Ignacio Peiro from the Instituto Cervantes for initiating this lecture series, which relates to the EU-funded research project SILKNOW on silk production and trade in Europe. And I'm also very pleased that Pedro Eusebio is also here tonight and be able to welcome you personally. Pedro, it's over to you.
Thank you very much, Professor Claudia Hopkins. It is an immense honor for Instituto Cervantes to have organized these three conferences in cooperation with the Soberan Center, the University of Valencia, represented by Dr. Cristina Portalés, the University of Leeds, represented today by Professor Cris Carr, all the European partners involved in SILKNOW project, and of course, thank you very much, Claudia, for your help and support all the time. The Instituto Cervantes, in its vocation to promote Hispanic culture in the United Kingdom and in the world, has a privilege allied by in the Soberan Center. On this program, some leading European universities and research centers are joining forces to show the role of silk as a vehicle for the exchange of ideas, technology, and in the creation of a global cultural dialogue. The fundamental value of silk exchange was its enduring testimony of great cultural, religious, and technological dialogue taking place along the many places where it was traded. Today, we will have Professor Cris Carr, who will give us another approach to the silk and the use of it. Thank you very much also, Professor Carr. Thank you very much to the audience, and I give the floor back to Professor Claudia Hopkins.
I'm delighted to introduce tonight's speakers. Our first speaker is Professor Cris Carr. He's Professor in Textile Technology at the University of Leeds, where he was head of the School of Design until September 2020. His work focuses on healthcare textiles. He is published widely through research publications and conference presentations. He's also a member of several editorial boards for international research journals. In 2015, he was awarded the Society of Dyers and Colourists Gold Medal for his outstanding contribution to textile and colour education, and he is currently a trustee on the Society of Dyers and Colourists. Cris Carr's lecture will focus on contemporary uses of silk, and his lecture will then be followed by a short presentation on the SILKNOW project by Dr. Cristina Portalés. Cristina Portalés is a Ramón y Cajal postdoctoral fellow at the Institute of Robotics and Information and Communication Technology at the University of Valencia. She holds an engineering degree in geodesy and cartography from the Universidad Politécnica de Valencia, and she also holds an MSc in surveying and geoinformation from the Technische Universität Wien in Austria. She is the author of over 90 scientific publications. She is a co-editor of the journal Multimodal Technologies and Interaction, and she is a board member of the association Ciencia en el Parlamento. Her research focuses on computer vision, augmented reality, data visualization, and digital cultural heritage. She is a technical manager of the SILKNOW project. So with this, I now welcome Professor Cris Carr, and I'm handing over to you, Cris. Thank you.
Okay. Thank you very much. To reassure and to perhaps offer an apology at the start, I'm Welsh, and for our Spanish audience, the Welsh are renowned for talking and talking and talking and not knowing when to stop. So I've made sure I brought an alarm clock to keep me on the straight and narrow. The title of my talk is Silk in the Contemporary Society, Beyond its Ornamental Use. And there you go. So there was a bit of a delay. Many thanks for the invitation to present at SILKNOW. Pedro has guided me in terms of trying to make it entertaining, educational, and short. And I will endeavour to do all three. What I'm going to talk about is a little bit about my history, my interest in silk, the nature of silks, the traditional uses of silk, and silk in, let's say, the modern era as a regenerated biomaterial and where it's going into the future. And I think it is a very exciting future for the silk fibre. My personal journey in 1984, in my first postdoc, I went to CSIRO, Division of Protein Chemistry, Wool Research in Melbourne, which was one of the premier protein research institutes in the world. And at the division, they had wool and leather research, and my interest was in the wool. In going to the division, it was explained to me that part of the reason for the lot of protein research that had been going on is that the protein chemists had sold to the Australian wool growers and the Australian government is that if they knew where every amino acid was, the sequence, the proteins within the fibre, then they would be able to engineer the wool fibre to give specific properties like fineness, luster, and crimpiness. And if you bear that in mind, it's now coming up to almost 40 years since I came across that objective. You'll see where I'm going with this. Went to the US Department of Agriculture, again working on wool and leather. And then 1992, I returned to UMIST, which is now part of the University of Manchester, and started again in wool and silk. 2002 involved in an EU fifth framework project monitoring of damage in historic tapestries. And it was the largest cultural heritage project at the time. And it was focused in on tapestries. The partners were Hampton Court Palace, KIK Brussels, and the Royal Palace in Madrid. And coming from a scientific background to better understand that tapestries in medieval times were the iconographic symbols of wealth and culture in medieval Europe. They were the bling of their time, fabulously expensive, and they were a statement. The project was to focus on characterizing the damage on the micro scale and to try to be able to predict when the material was going to fail. And this is the sort of degradation and the damage you can see, and you can see some of the rips on the right-hand side. And for the conservators, this was extremely important because the tapestries were very heavy, and to predict the rip and failure of the tapestry was something that they couldn't do. So it was very similar to England winning the World Cup in football again. For the conservators, they knew it was going to happen, but they hoped it would never happen in their lifetime. And as a Welshman, I similarly hope that England do not win the World Cup in my lifetime. These are some of the components in the tapestry. You've got wool, you've got silk, and you've got metal threads. And in this metal thread here, it's silver, but you also got gilt, which is gold covering the silk, or covering the silver, and a central core of the silk yarn. The yarns could be single wrap, double wrap, or triple wrap. The greater the number of wraps, the finer the metal yarn, and the more visual the impact that said that it costs more. When people talk about nanotechnology as if it's a new thing, it's not a new thing. And in medieval times, they were able to produce very, very thin sheets of gold. And we can see here in the SEM, you've got the silver, dark, and then this white surface layer, which is the nano layer of gold. So How they did it, nobody really still knows, but the fact that it's there, and we were trying to characterize the damage. The second project on the tapestries was a virtual colour regeneration of one of the tapestries at Hampton Court Palace. And what we were looking to do was digitally archive the tapestry, and on the front of the tapestry, the natural dyes have faded, and on the back, because it's not been exposed to sunlight, you've still got the vibrant colours in an undegraded form. So by digitally archiving the front and the back, what we were hoping to do then was to project onto the tapestry in Hampton Court Palace what it looked like in its original state 500 years ago, compensating for the variable color. One of the things you see with the natural dyeings on tapestries is that the green is produced from indigo and yellow weld. The weld is very photosensitive, so you end up seeing a bluegrass, very much like you observe in Kentucky. That's what the tapestry looks like now. Nothing impressive, but nothing really to write home about. And then when we projected onto the front of the tapestry, you had the whole vibrancy and the original colors, and to see what it looked like and how in its full splendor. Was it a success? There were about 1.5 million visitors to Hampton Court Palace, and it was deemed as a huge success. And we won an award from the Museums and Heritage Award for Innovation in 2011. And in the middle, at the bottom, you can see Henry VIII and Catherine of Aragon looking at the tapestry there. So let's move on to traditional uses for silk in clothing, kites, parachutes, in sutures. On top right, we've got Queen Victoria's wedding dress and clothing from around the world. One of the stories you pick up early when you start looking at what are the uses of silk is the wearing of silk by the Mongol army. They were much lighter in their army than the European knights. They had a lightweight laminar leather or iron laminar armor, and underneath a tightly woven silk shirt. And the reason for the tightly woven shirt was to not stop the arrow, but to wrap a pocket around it. And when the arrow was then pulled out, there was less damage to the flesh, and the soldier survived. There were no loose fibers, and any residue was biodegradable and didn't cause the wound to go septic. To give you an idea how strong silk is, when I did my PhD, I had to try and grind up some wool in a mortar and pestle with liquid nitrogen. Easy. You try it with silk, it's impossible. It's incredibly tough. The other historic application is a bulletproof vest, and we've got a picture there of Casimir Zeglin wearing a lightweight silk vest with multiple silk layers, being shot. He survived happily, and he made a business out of it, selling the shirts for around $800. He sold one to William McKinley, the US president, and if he'd worn it in 1901, he probably would have survived. Similarly, Archduke Ferdinand had a silk bulletproof vest, and if he had worn it, who knows what would have happened. Obviously now the gun technology is improved. The silk vests don't function in that way. We've got Kevlar fibers, and in terms of marketing the vest, they're now regarded as bullet resistant rather than bulletproof. So the sources of silk, we have the commercial culture, sericulture from silkworms. We also have silk produced by spiders, over 30,000 species of spiders. And that's where the modern focus has gone in on trying to understand the more sexy spider silk and how that can be used to produce high strength materials and biomaterials. The silk filament consists of repetitive protein sequencing and specific amino acid sequences that are associated with mechanical properties. In the spider and the silkworm, we have silk that is associated with cocoon formation, nest building for traps, for web formation, safety lines, and egg protection. For the silkworm, it's a much simpler end use scenario. Which came first, the chicken or the egg? We've got the life cycle of the silkworm there. Let's go with the exciting bit. We have the adult moths who mate with each other. The female moth then produces the eggs. The egg hatch, out comes the caterpillar, and the caterpillar eats the mulberry leaves and goes through a whole series of molting processes. And after the fifth, then emerges as it's the final caterpillar form. The caterpillar then spins the cocoon and goes into the pupal stage. After a period of time, it emerges as the full-grown moth, and the whole process starts again. In the sericulture, what we have is that the cocoon is collected and unwound, and we produce the filament that we're actually interested in. The understanding of that conversion of a liquid silk protein into a solid is partially understood. There's still a lot more to learn, and one of the drivers has certainly been trying to understand the genetic engineering of the silk in its production. There's a picture there of the silkworm silk that has in its raw state. We've got the central fibroid, which is the filament we want, and it's coated with the sericin. We need to degum that sericin to get at the usable silk fibroid. For the spider silk, similar sort of product and visible material. There are spider farms, but it's a little more difficult because spiders are cannibalistic, and it's very difficult to get them to play nicely. The table at the bottom shows the comparison between the spider silk and the silkworm. For the spider, you've got up to 6 types of silk. For the silkworm, 1 comes out of the mouth of the silkworm, comes out to the backside of the spider. Domestication possible with the silkworm, not with the spider. We have the central protein for the silkworm is fibroin, for the spider, spidroin. There are distinct differences in their amino acid composition and the short polypeptide sequence. One of the interesting things I've found out, the differences between the silkworm silk and the spider silk, is that if you put the spider silk in water, it super contracts by up to 44%. And that must be related to the fact when you've got the spider web, if there's any water goes onto it, if it doesn't adjust to that, the web will sag. By absorbing the water, it contracts and keeps the web taut and dries out slowly. The key thing for the spider silk is the polyalanine sequencing, which gives rise to the crystalline regions and the tough hard bit. The elastic component is more related to the amorphous regions within the filament. Typically within the silkworm silk and in the spider silk, we have a mixture of crystalline regions aligned with the filament axis to give the strength, and the amorphous domains to give that flexibility. There are 3 types of protein in the silk filament. The major one that we're interested in is the heavy chain, which is the glycine, serine, glycine, alanine sequence. I've re-mentioned that protein chemistry mission statement. When we come later on to look at the new generation of silks, that understanding of the sequencing and the protein distribution will be vitally important. And a lot of fundamental work has gone into understanding the protein sequence, structure, and the relation to mechanical properties. Classic picture there of differentiating between silk and wool. With wool, you've got the alpha helix. With silk, you've got the beta pleated sheet. Typically with the silk, you've got good flexibility, good strength, relatively little extensibility, but it can be engineered in. So the modern uses. For fabrics, what is attractive of the silk fabric? It's still out there, it's a premium product. Smooth, soft. The fabric feel is dependent on the fabric construction to some extent, but the base material does have that high luster and softness. Fabric strength, depending on the structure, cool and warm. Biocompatibility, when we look at the healthcare aspects, something to be biocompatible has to not be rejected within the body and ideally be absorbed in. So healthcare is a huge area for silk. In my introduction, I've worked with Croda for many, many years on hair research. It clearly is of an academic interest for me, and similarly working with Unilever on hair products. And so in that space, research space and product space, silk is very important. It's used on skin, on hair to give hydration and moisturizing, smooth, soft appearance, and high luster. And the last application, again, still people looking at protection. Traditional healthcare for silk used in sutures, and an example there of the sewn and the metal clamping. In developing this talk, I actually came across a fabulous paper on the treatment of traumatic brain injury in the Roman army. And the reason for it was a gentleman, Claudius Gallin, in this time line, 150 AD, who documented the use of silk sutures in repairing the beat up Roman soldier. And as we move through to 150 AD through to the 1930s and 1960s, where people were trying to better understand the use of silk and what you could make out of the silk cocoon, that better understanding of the use of silk in healthcare expanded. And then in the 1990s, the research developed by Vollrath and Kaplan looking at recombinant spider silk and where that could be a material of the future. Classic Shakespeare play. It was a film, but it was in the first place a play. A Midsummer Night's Dream, and Nick Bottom, who says, "I shall desire you of more acquaintance, good Master Cobweb. If I cut my finger, I shall make bold of you." So silk used in medieval times as a healthcare, or a spider silk web used as a healthcare material. So as a raw material for healthcare, silk, biocompatible, non-toxic, non-irritant. Some of the modern materials that are biocompatible, when they degrade, give rise to irritancy. Silk doesn't have that problem. And again, good mechanical properties, but we need to remove the sericin. That outer coating can cause problems in terms of healthcare. And this is the sort of typical production of regenerating the silk. On the first stage, to degum, remove the sericin, boil it in alkali, and you see a 25% reduction in the weight. Dry, dissolve in lithium bromide. Lithium bromide is a very powerful solubilizing solution for proteins. Dialyze to take out the waste materials, centrifuge down, collect the supernatant, and then add to a mold and dry overnight, and you get your fibroin film, which you can then use as a healthcare material. And I apologize if anybody is of a nervous disposition. What we have here is rabbit skin, where they have looking at grafting and taking skin off, and they've applied silk fibroin film, a PLA membrane, and a silk fibroin coated sponge onto the skin, and they've also got the blank. And what you observe that with time, the silk fibroin film heals more quickly. The curve on the right-hand side shows that after about 12 days, the wound size has completely closed. The other materials are slower, and one of the advantages of the film is that it has better moisture vapor transfer and liquid control and adhesion to the exposed skin, and causes less scarring. Just to show that it also works on human skin, we have the same situation here, the fibroin film, the Sidai silk fibroin sponge, both working nicely, but the film is actually better. Another example of the use of the silk fibroin in healthcare is in transdermal application, and developing a patch with very sharp needles. The patch and the needles are made out of the silk fibroin, and they are impregnated with the drug that will be used to penetrate via the skin into the body. And on the left-hand side, we've got the aluminium master mold. We pour the polydimethyl siloxane polymer in there, we cure it, and then we can pour in the drug-loaded silk fibroin solution, dry it, cure it, and we're then left with these very sharp needles that contain the drug. The bottom right pictures show the human skin with the needle as penetrated, and we can get the drug to actually permeate through the skin and deliver in an effective way. In this particular case for the model, they used an enzyme, horseradish peroxidase, and when you put it onto the collagen mold, you see the penetration into the collagen, which has got a dye stuff in it, which complexes with the horseradish peroxidase, and you see the blue color coming through. What you can also incorporate into the needles are antimicrobial reagents, so that you don't get any growth around where the needle is penetrating, and it keeps the patch clean of any potential microbial growth. So you're creating multifunctionality in these patches. Just to give a broader idea of what you can do with these silk cocoon materials, once you solubilize them, you can produce structural materials, you can produce mats, hydrogels, sponges, tubes, nanoparticles, all with multiple uses in healthcare and in the cosmetics industry. This is an example of a silk fibroin screw that's been manufactured and is used in this particular case, a rat femur fracture, where they've inserted it in to aid in the recovery and the repair and the bone growth, and ultimately the resorption into the body as the bone cells actually regenerate and take over after the healing process. And the bottom two slides show the screw gradually resorbing after 4 weeks after the operation. So used as a very effective structural material. This example here is a vascular graft made out of an electrospun non-woven. Electrospinning is a technique where you can produce nanofibers with very high surface area and use that to form very tightly impermeable materials. And in this case, it's used as a vascular graft. Looking at the graft at time 0, then 6 weeks and 24 weeks, we see cellular growth on top of the graft and within the graft, and gradually it becomes part and integrated within the aortic blood vessel. There's no staining when you look at it with the silk, and no buildup of fibrinogen. With the alternative PTFE stent, you see some clotting, so it's not as good as the actual silk version. Also came across this commercial product, which is, I suppose, the equivalent of Botox for your ear. For your vocal cords. This is Silk Voice, which is a silk fibroin injectable material that can go into your vocal cords. And on the bottom, we've got the vocal cords where it's actually open, and you can see the trachea below. And then when it's shut, you can see that it's actually closing very tightly. If you have a lack of substance in one of those vocal cords, it can result in you losing your voice. And by injecting this silk fibroin, you can get the bulk back in and return your voice. This is an example of another implant. It's for the ear canal, and it's to combat otitis media with effusion. Essentially, when your middle ear has got poor drainage, it can cause problems. And one of the ways to overcome this is to put in a tube to aid in the draining. And the example I quoted there is a Shepherd Teflon grommet designed for 1 to 2 years to treatment, and then it will self-extrude. The problem is that self-extrusion can be unpredictable or not happen at all, and that can cause problems. What was done was to look at polylactide alternative manufactured tubes. The trouble with those is that they degraded and caused inflammation, whereas with the silk fibroin version, you get very effective performance and no problems in use. You can also coat it with an antimicrobial, which will stop the growth of Moraxella catarrhalis, which apparently infects the ear. So all in all, a very good solution. Another example of using nanofiber mats, and the example shown here is in the green mat. And what it's used, we've doped it up in this particular case with riboflavin, and the patch can be put onto flesh, in this particular chicken breast, and you get a visual color change as the riboflavin passes into the flesh. Similarly, if you irradiate with a laser, you can actually visualize the riboflavin has actually penetrated into the breast. And again, you're looking at a controlled release of drugs into the body. You can also use the silk fibroin mats for external sensors. And in this particular case, you're looking at the potential exposure to dangerous vapors or gases, and hydrochloric acid or hydrofluoric acid interacts with the sensor, the colorant in the nanofiber web, and changes color with time and with concentration. And there you can see its integration into the glove. A comparison between spider silk and silkworm silk. The red line on the right indicates that the spider silk breaks at much higher stress. It's also quite extensible. So as well as being not breaking, it's got stretch. With the silkworm silk, straight out of the cocoon, it's got, that's the black line, it's got much lower strength and less extensible. And what they did was to essentially mechanically draw the silk out of the silkworm at higher speeds and look to align the protein chains more effectively and increase its strength. And that's what they did. However, there's a limit to how far you can go, and the optimum level was at 13 millimeters per centimeter squared. But that's the sort of thinking that was going on, is can we draw the silk out at a faster speed and produce strong fibers? The other approach, which was, if we can't pull it, can we feed the silkworm something that will make it stronger? So they sprayed onto the mulberry leaves graphene or single wall carbon nanotubes. The silkworm ate the graphene and the carbon nanotubes, and what we see is that it's incorporated into the silk, and for specific types of graphene and carbon nanotubes, you do get an increase in the strength. There's also the question, well, if the silkworm is eating the graphene, does it all go into the silk, or does it go out through the excrement, out of the backside? And the answer is it's both. Is that the graphene that the silkworm eats, as well as being incorporated into the silk, is actually extruded out of the backside and is lost not in a particularly useful way. The reason I mention this is that there's been some recent work looking at the Galleria moth, or greater wax moth, which produces silk in its own right. And the Galleria moth is a major parasite in honeycombs and causes millions of dollars of damage. The eggs are laid in the hive, the larva burrows through the honeycomb and eats the wax comb, which is very hydrophobic, long chain fatty acids and hydrocarbons. And somebody had the idea, well, polyethylene is also very long chain hydrocarbon. Can the moth eat the polyethylene waste and incorporate it into the silk in a useful way? Good idea. Unfortunately, the latest research indicates that the Galleria moth, all it does is digest the polyethylene waste and then put it out in its excrement. So there's still work to be done, and hopefully it could be a sustainable solution to dealing with some of the polyethylene waste out there in the environment. So the next generation of silk uses, and that is focused in on microbes. Most of the research in this area has gone into spider silk, and the idea was to extract the DNA from the spider, identify the DNA that codes for producing the spider silk, insert it into a plasmid or virus after snipping the virus DNA, introduce that into E. coli or other bacteria, and then ferment the bacteria, which will then generate the spider silk or components of it, which will then which will then self-assemble and actually produce the silk filament. That's I've got one eye on at the time. There you can see a more elaborate picture, which indicates that the recombinant DNA will produce the recombinant protein that will then self-assemble. You can spin it into filament or into nanofibrils and hydrogels. It is extremely technically difficult, and there are problems in terms of putting these long sequences of repetitive DNA into the plasmids or the viruses, but there's been success. I'll just cut through to this. The commercial reality. There are companies out there now, and there's Bolt Thread, but I've focused in on Spiber, who are producing a spider silk fiber. They've determined the genetic sequence, they've incorporated it into the microbial DNA, and they are now using large fermentation vats to produce the protein powder. That protein powder can then be spun into multifilaments or monofilaments and be used. This is the glossy brochure from Spiber. It shows on the left-hand side the fermentation vats, the brewed protein that's produced, spinning the fiber, getting the alignment of the crystalline chains, and then this parka that has been manufactured as a prototype. There's an inauguration ceremony, or there was an inauguration ceremony in March 2021, Spiber's first mass production facility, and it will go into operation later this year. They've also signed development deals with Archer Daniels Midland Company in the States, who are experts in fermentation technologies, to look at improving and optimizing that process. I put at the bottom, they recently got 162 million pounds investment through Mitsubishi Bank, Morgan Stanley, but the work's been going on since the early 2000s, so it's significantly more than that. To try and get acceptance of the materials, they're obviously going into the haute couture market, and there are examples of clothing that's been made out of this regenerated silk, winter and summer, fabulous outfits. They've also signed up with an agreement with Goldwing, who make skateboards, and the idea there is to blend bamboo as sustainable material with the brewed protein and produce a composite material that has the strength of the silk and the elasticity and the bendability of the silk that can go into the boards. The big one is looking at the brewed protein, the spider silk, as a regenerated bioplastic, to move away from the traditional petrochemical plastics and be able to mold plastic materials out of the protein. And the results are very encouraging. The other advantage is that the protein plastic will be biodegradable and there will be less impact on the environment. Conclusions. 1955, the first International Wool Research Conference was in Melbourne, Australia. There were 4 Nobel Prize winners presenting at that conference. 2 of them were double Nobel Prize winners. That's how important the protein fiber wool was. Will history ever repeat itself? Will you have a Nobel Prize winner attending another wool conference? It's unlikely. Could there be a Nobel Prize winner in the development of these silk bio-based materials? I'd have to say maybe. The jury's out, but if they do come to a large-scale commercial fruition, it will be a game changer. And you'd like to think that those protein chemists and producers will be recognized. So the future for silk, granted it's not silkworm silk, but it is silk nevertheless, is very exciting. The ability to design fiber properties and performance through genetic engineering is key, and a lot of the groundwork has been done. I was talking to the other speakers earlier on about stepping down as head of school and entering the twilight era of my career. I've been through a personal journey recently, is that I looked back at my first days in protein chemistry and recognizing the ambition of being able to understand, manipulate, and produce designer fibers. And it's lovely to see that in the silk area, it looks as if it could be done, and that the microbial technology will allow us to disengage from supply chains and create a new supply chain for producing fibrous materials and bioplastics. Thank you very much. Not too bad on time, I think. So thank you.
Perfect, perfect. Thank you so much. That was so interesting. It has really opened my eyes on silk. I have a completely different understanding. now, thanks to you. And I have a lot of questions, and I'm sure the audience is as well. So please, again, type your questions into the chat.
Okay. Right.
And after the next talk, we will have time for Q&A. So I'm now handing straight to Cristina Portalés. Cristina, would you like to share your slides?
Yes, of course. Just a second. Okay. Okay, I think. Can you see my slide?
Yeah.
Okay. So thank you for organizing this talk, Claudia, and hello to everyone. So I'm going to talk about the virtual loom, which is a software that we have developed in the scope of the SILKNOW project. And just briefly, how it works. So basically, this software is for giving a design, giving a picture. We can reproduce a 3D representation of this design. And what we need is an image of whatever image, if it is a textile or not, it doesn't matter. We need a design, an image. And then the user needs to define the dimension and the weaving technique and other settings for the software to understand what the user wants to produce with this information. And then we have, in the middle, we have some basic image analysis and 3D stuff in order to reproduce the final representation. So basically what we do with this image analysis is to discern between the different areas that we can find in the image. Let's say how many colors this image has, because this is the number of different yards that we can find in the original fabric or textile. So the user can define the number of areas, then he or she can select from a number of 3D models of yards. These models are very basic. They are not so much detailed like in the reality, because we are producing a software that has to run in real time and we need to provide simplified 3D models, let's say. And then we have also implemented kind of waves and which are linked to different weaving techniques. So the thing is that, of course, I'm not an expert in textiles. I'm from computer science. But in SILKNOW, we work with experts in textiles and experts in our history. And they have translated us all this knowledge, how these textiles were woven, how what are the properties of the yards, what yards were used in this 15th century, 16th century, etc., and what yards were used for what weaving techniques. So all this information, it's inside our model for the reproduction of these 3D representations. And one of the outcomes that we have also is that we can print the 3D representations of the fabrics. So basically, these are some of the weaves that we have implemented in our software tool. And these are the weaving techniques. Of course, we don't have all the possible weaving techniques. We have focused in some of them which are representative of the 15th century to 19th century. So these are the ones that we have considered. And just I give you an example of an espolín, which is a term used in Spanish. And we can see here the background and the foreground of the espolín, how the yards are interlaced, what is the direction of the yards, which one is on top, which one is down. So we, as computer scientists, we have to understand all this geometry in order to transfer this geometry to the computer, and in order to try to to provide a 3D model which is very representative of these techniques given a specific design, a specific image. So it's like, so the virtual loom does not provide a 3D model like you would have with a 3D scanner. With a 3D scanner, you need the textile and you need to scan the surface. With the virtual loom, we only need an image and we have the whole 3D model of what it could be in the reality. So this is the difference with a 3D scanner and the virtual loom. So of course, we have also, some of our partners had these textiles and they have provided us with these textiles, and we have done some optical studies in order to see more in detail what was the relationship between the different yarns in order to understand this geometry and to see how, for instance, when we had these metallic yarns, what happens there? How are they geometrically constructed? So we had first to understand all these things before we could produce this 3D modeling. And here I'm not going to go into detail, just to say that this image analysis is different depending on the weaving technique that we apply, because they have different geometries, let's say it. So we need to internally treat them differently. And if you want more information about how this works, I have here put a recent paper that we have, and there is everything. It's very detailed explained. So here is just an example. The image analysis we do is very basic. We just discern between different areas. So here there are two areas, and from this image we produce the 3D model. Here the user defines also two areas, and that is this. You see these squares are skipped because there is a high contrast between this red and everything else. So we can produce a good image with only two areas. And this would be, this is not a very, it's an image with not a very high resolution, but of course, this is like 6 areas, and the user says, I want to produce a 3D model with 6 areas, and this is the result. And here we have also some yarns that we have modeled with the radius, with the number of yarns, with some basic characteristics that we have defined for these yarns that were used in the weaving techniques that we have used for the virtual loom. And here I have an example, but I think I'm going to directly show you how it works with the virtual loom. First of all, you have to know that this software is open access. You can download this software, and you can also download the code. It's everything open. So first step, I just select an image. So this is an spooling. I'm going to select, I can select the area that I want to weave. I'm going to select a small area because I'm going to show you, I want to show you a basic example. So here is the image that I have selected. I can do this. I can also do that. Okay. So I can change slightly the design, the original design, or I can keep the original design. Okay, so let's see, I want to weave this. So then I can select the weaving technique I want. So if I select the mask, it's only made of two colors, 2 yarns. So I can only select 2 areas, and I apply, and this is an image with 2 areas. And then I say next, and I say, okay, this is I want this to be my background. Then I can change the width if I want to change the width, or I can just leave the default one. Okay, let's see this width. And just I can generate the 3D. Okay, so this is the 3D. I can rotate the image. Okay, I can zoom in and see the width. I can see this. I can change the resolution, high resolution. I can put low resolution if I want to see how these jars go up and down in more detail. But of course, I can go to high resolution. Anyway, now I'm going to come back. And I'm going to select another technique. So now I select the spooling. With spooling, I can select more areas. So I want to produce a 3D model with 3 areas. And this is, it's not very clean, this image, but okay, it's 3 areas. And then I can select the background. I can also change, I can change the color. I can change maybe the jar, but I will leave like here. And of course the width. Here I can generate the 3D. So you know, this is quite different. This is very similar to the image that I showed you before, how this spooling was made with the jars in this direction, which is different from the mask. Okay, and you can see also. And of course, you can take a picture and you can export the 3D model for the 3D printing. Okay. So now I'm going to go back to my presentation. Just very quickly, just to finish it. So, okay, this is the example we have seen, more or less. And this would be like the 3D model coming out from for the printing. So as I told you, this is an open source project. We have different versions. So we have the standalone version for Mac and for Windows. And here you have the address for it when you can download it. We have also web version. You can run the virtual Loom through the web. You don't need to install anything in your computer if you don't want. And it's also integrated in AdaSilk. So AdaSilk is a exploratory web engine that we have produced in the SILKNOW project. Here you have the address. So for any of the image that it's in AdaSilk, you can select the image. Oh, sorry. You can select the image you want, and the 3D, you can just reproduce the 3D model for a given textile. And of course, you can produce 3D model for your own textiles. You don't need to have, or for your own designs, you don't need to have a real picture of a real textile. You can just have your design, your picture, your photograph, and you can just weave it with the virtual Loom. Yeah, just a picture. And here, just put a list of references if you want to have more information of our research. And of course, if any of you have questions, we will be very happy to answer you, whatever. Thank you.
Thank you so much, Cristina, for such a fascinating paper as well. Again, new insights, and I have a lot of questions, but there are already some questions in the chat, and so I'm just going to start with them. These were fascinating papers, as we can tell from the questions. There's a question from a Chris who's asking, what are the barriers to making synthetic silk-like material that has similar functional properties of silk, but without organism extraction or bacterial cultivation? What are the closest leading candidate materials that are available commercially and be 3D printed as filaments?
when I focused in on the microbes, there's been other research where they've been looking at actually using goats to secrete milk and to extract the proteins out of the milk. That's an alternative. I think the microbes allow the opportunity for scaling up. How you get to that point of producing the protein is, I think that currently the state of the art are the genetic engineering of microbes. They're the easiest to do. It's still a lot of work to actually get to that large scale production. In terms of the performance of the filaments, you're still very much tied into those amino acid sequences, and the polyalanines appear to be very important in that. And similarly with the stretchability, it's the glycines and the prolines that are providing that performance. Are we at that commercial stage yet? They're investing an awful lot of money. I think one of the chat questions came through: how expensive is going to be this process or this material? I've regularly said to students, go up the library and you're going to see some fabulous papers, really, really clever, in the textile journals. And you're going to say, why have I never seen that actually in production? And the real answer, the answer is how much is it going to cost? The textile industry is not a philanthropic exercise. It's hard-nosed, and you look back over the history of the textile industry in Europe in particular, and how there's been the shift to the east, and that was on the back of cost. Similarly with weaving, Lancashire was the center for weaving in the world. However, there was a lack of investment, and the Americans invested in new looms. India, China, and the weaving industry in the UK is a shadow of what it used to be in the 1930s and 40s. So in terms of what's the production route, it will come down to money. And I'm sorry, but that's the where silk has been very effective in placing itself is that it's regarded as a premium value product. Similarly, in the healthcare area, these materials cost a lot of money. So there's a potential very good return on the investment. When you start going into bioplastics, you're moving into a commodity area, and that will require that the bio silk plastic has to be very cheap. And that's the dilemma: is do you go for premium end or do you go for commodity? It very much depends on what the consumer wants and how cheaply you can produce it.
Thank you, Chris. But what emerges is that I really had no idea that silk is so well beneficial in all areas, health, the environment, and yeah. So I hope, I think it gives hope.
I have committed sacrilege. I am a wool man through and through. I was a wool PhD student from Woolmart, and for me to stand up and say silk looks really good, it hurts. It hurts.
But it does. Well, I think you've answered the question about economic viability from Mary Brooks. There's one more question about from Sandra. Could you talk a bit more on the use of silk within surgery? You showed these interesting images on the rabbit and the.
And I mean the papers that I drew those studies from, I've listed in the talk and acknowledge those. The healthcare area and the research, there's an awful lot going on. Whether these materials they look very promising, whether they're actually used in a commercial environment, to be honest, I'm not certain. The Silk Voice, and I think it's Sue Freggen, is the spin-out company from Tufts University in the States, and it's a spin-out from David Kaplan's research group, and they have commercialized these products. There's a lot of similar work going on with collagen and modified collagens. They're out there. The extent to which they're used, I'd have to say, I'm not 100% certain, but the fact that they have such promising results would suggest to me that they are being used. And you're starting from that base layer, that the silk protein, which has been known for thousands of years, is a very good biocompatible healthcare material. And there's a reassurance in using that material. The other attraction to it is that what they're also doing with these regenerated silk materials is incorporating in other functionalities where you can get cell growth and adhesion or cell repellency, where, say, in a vascular graft, you do not want clotting. So I think the designer element of it is really encouraging, and as the technology develops further, I think the use of silk will become more embedded. Yeah, it's as simple as that. I think, yeah.
We thank you. And there's one last question for you. Food safety. Are silk nano needles used in that as well? Do you know?
Ooh. I don't know the answer to that. I did in terms of food. Oh, I don't know. I would imagine that it would be quite difficult to digest silk in the gut, but it's pretty acidic in there. I think generally the proteins that go in need to be digestible or in a relatively I'll check up on that one. Thank you for asking. I don't know. I've never come across silk as a food.
But it wouldn't surprise me after all these beneficial things that silk can offer. It's incredible that these little insects, spiders and silkworms can produce this.
When
So,
in seeing that the silk is the silkworm has been fed graphene and carbon nanotubes, and the fact that they can incorporate it in, is that particular approach is not particularly new. When they were doing the wool research back in the 1950s and 60s, there was a suggestion: what can we do with waste newspaper? And they were feeding the waste newspaper to the sheep because it's cellulosic. Why can't the sheep digest the old newspapers? Yeah, they could do it, but you need to supplement it with other nutrients, and then it becomes, well, it's going to cost more money to do that. Get them out in the fields.
yeah.
Yeah.
Here, it's a couple of questions for Cristina.
Right. To detect bacteria. Yes, I think that is definitely doable, because you would then be able to, and they do that in the presentation, is that you can put sensors, chemical sensors onto the surface of the fibers, and those will then, when they complex with the bacteria, can give you a color change. So yes, that's entirely doable. And it's in terms of the packaging, that should be relatively simple to do.
That's great. A couple of questions for Cristina. Could this tool be useful and easily used in museums? And for developing the tool, what about interdisciplinary work concerning both tangible and intangible parts?
Okay, so for the first question, yes, this tool, of course, can be used in museums. So think about that with this tool, you can show the internal structure of the fabrics without needing to touch the fabrics. So, you know, these silk textiles are fragile. So when visitors go to museums, maybe they want to know more about these techniques. And this is a way to showing that, and so they can also manipulate the 3D and navigate through the textile. And of course, this is not an invasive study, or so for the museums, they only need to take a picture of the textile. They don't need to buy expensive devices or whatever. They just need to have a picture. So with this picture, they can produce this 3D model. And regarding the interdisciplinary research, this has been a key in producing this tool. So in the project, we have a partner that is Garin, that they are still weaving with the jacquard looms. And we visited the fabric, and they taught us, they show us, and we could talk with the artisans how they were producing these textiles in the same way as in the 15th century, in the 16th century. And this was really incredible. The beginning, it was really difficult for us to understand everything. And there's a lot of specific vocabulary and a lot of things that are, and a lot of decisions that the artisans do while they are weaving. And so this was really, for us, it was really amazing to know all about this our intangible heritage, intangible because the fabrics are tangible, but how artisans weave is this intangible. And we were trying to put in this 3D model also these decisions that artisans do. For instance, in the Espoline, the yard goes from here to here, but when do they cut the yard and they start a new yard? All these things we have tried to put this in this 3D model. So for us, it was really an incredible work of interdisciplinary work, of course. Thank you.
Very, very interesting. I know, I mean, you've mostly worked on on this database, on this tool, on this analytical tool, but taking a step back in terms of the whole SILKNOW project, and there were so many different countries involved. Is there an overall concept about how, you know, silk production developed, which place was more important or more important than another one? Last week we talked a little bit about trade and how silk came along, but in terms of weaving or the work that you've been doing on detecting patterns and techniques.
Yes, the truth is that we have asked our experts in textiles, because I'm not an expert. I cannot say which one are the most representative of these centuries, but we have experts that have told us these are the most representative, and there are others like velvet that we had no time to do that. So this is maybe for SILKNOW 2.0, the next step. But our idea is that the ones that we selected were very representative of these centuries, and we could do a very good work to navigate deeply into these weaving techniques and to try to be as much precise as possible. For instance, we have collected all the different weaves that were used in a specific weaving techniques, and this is reflected in the software. So if a user selects lampas, he or she will have a list of possible weaves, not all the weaves that we have implemented, but only the list of possible weaves that were used in lampas for those centuries. So this is everything inside the virtual loom.
It's really fascinating. So it means then people can, or you can find connections between weaves in made in
Yeah.
different places at different times and suddenly detect similarities and then
Yes, and of course this is also integrated in Ada Silk. So Ada Silk is not finished yet, but when it will be finished, we have special temporal maps when you can see also, if you look for the maps, for instance, and you will see in this map all the objects that we have collected from the museums, distributed all over the world. So they come from here, from there, and we show the relationships between them. So for instance, if you want the damask that has flowers, you can select I want the motif to have flowers, which are the other damasks that have flowers, and you will find these relationships in the maps. So it's like everything is connected at the end, and we are trying to show these connections in a visual way and in an interactive way. So people that study silk heritage have another tool that they can use and for their research, their investigation, and of course we are open for improvement. So if there are experts in silk textiles from the centuries we are talking about, please tell us if you have suggestions or if you think something can be improved, because we are open to receive all the feedback. Okay, thank you.
okay. Well, thank you very much. Thank you, Cristina, and thank you again, Chris. It were wonderful, both wonderful papers and very different. And I think they've opened up new dimensions of silk, and we're really grateful. So thank you. And I also want to thank Pedro Eusebio again from the Instituto Cervantes for co-organizing and co-hosting
you.
sessions. And thank you all for joining us tonight on a Monday evening. I hope you have a nice week. Please do keep visiting our websites of the Instituto Cervantes and the Subaran Center for new events, and also the videos of the 3 talks. They will be on the Instituto Cervantes website and hopefully also on the Subaran Center website. So thank you again and have a great week. And thank you.
Thank you.
And
Thank you, Cristina. Thank you very much.
Bye.